Hello, welcome to CE 3305 Engineering Fluid Mechanics. This is Lesson 11, Part 4. And the subject of this lesson, or this part of the lesson, is similitude or similarity modeling. So, in many fluid mechanics studies, or many real engineering studies, we construct small models of our full-scale operation to examine the behavior on those small models, and we use similarity relationships to scale up the responses of those small models to full scale. And so similitude is the theory and art of predicting prototype performance from model observations. The theory involves relating dimensionless numbers to models and prototype scales, so it's a second reason for dimensional analysis, actually. A practical example are pumps. Pump curves rarely reflect actual measurements, but instead they're representative of types of manufacturers' pumps monitored at a handful of operating points, and then similarity relationships are used to construct the pump curves for pumps that have similar morphological structure to the actual pumps but may never actually get measured, or maybe a single operating point. So we use similarity laws to adjust to actual applications. So there's several different kinds of similarity. The first one that we'll examine is something called geometric similarity, and that's where the length scale of the model and the length scale of the prototype have some relationship, and here we're calling it L sub r, the scale ratio. So when you go to a store and you buy a 1/72 scale plastic model of something, what it means is that one length unit on the plastic model represents 72 length units on the real object. And many models actually have this basic geometric similarity. It's the most obvious similarity. So the scale ratio, L sub r, is just the ratio of the two length metrics. If we're talking about areas, then it's the scale ratio squared. If we're talking about volumes, it's the scale ratio cubed. So that's geometric similarity. In and of itself, useful, but not terribly adaptable when we start talking about flows and other dynamic relationships. Second type of similarity is called kinematic similarity, and this is the requirement that the relative velocities of the moving parts in the model share the same relationship as in the prototype or the full-scale situation. So if we look at a time ratio, whatever time elapses in the model divided by an elapsed time for the same kinematic behavior in the prototype, that ratio is called the time ratio, T sub r. I like to call it a characteristic time. We can discuss velocity ratios, and velocity ratios incorporate length ratios and time ratios, and so the velocity ratio can be thought of as the length scale divided by the time scale, still having the concept of velocity, and that's called a characteristic velocity. Sometimes we have to operate models in weird geometric similarities where the aspect ratio is vertical to horizontal, or distortion along one axis is implemented to allow us to operate the models in a reasonable amount of time. Continuing with other similarities, if we look at characteristic accelerations, they ultimately are the length ratio divided by the square of the time ratio, and a characteristic discharge will be a length ratio cubed divided by the time ratio. Kinematic similarity is important with hydraulic machinery. The angular velocity, which has dimensions of 1 over time, is a really important property when we're talking about hydraulic machines. And so there's effort spent on producing proper kinematic ratios. The next and most severe type of similarity is called dynamic similarity. And this is where we require that the model and prototype have exact relative forces applied to the masses in the system. You can think of that as the force in the model divided by the force in the prototype. Those equal some constant, and that constant is preserved throughout the similarity process. in our textbook, pages 303 to 305, uses a spillway, and the pressure and shear forces on a spillway as an example. It's a really good read, so I recommend reading through that. It will clarify a lot of the issues involved in similarity. In that particular example, they start with gravity ratios, and they have the force of gravity in the model divided by the force of gravity in the prototype, and we want that to equal some constant. It'd be nice if the constant's 1, but sometimes it isn't, and so we would use that. We basically adjust masses, see, in the model, because we can't really adjust the prototype. Otherwise that makes it a model, and it's not very interesting. Another thing in kinematic we're interested in is often preserving the Froude number, at least in that example on the spillway. They go to the trouble to make the Froude number in the model identical to the Froude number in the prototype. That imposes certain requirements on the actual fluid viscosity and density. We also would require the friction ratio to be equal to some constant. Oftentimes in dynamic similarity, we also want the Reynolds numbers in the model and the prototype to be the same. Pressure ratios, we would want the pressure coefficient in the model to equal the pressure coefficient in the prototype. So these equalities right here, that, and that, Froude number scaling preserved, Reynolds scaling preserved, and pressure coefficient scaling preserved, imposes some limitations on the actual operations of the model. Dynamic similarity is not always achievable on this planet. So for instance, suppose we had a river model like the Mississippi River, and we want to model it exactly using preserving dynamic similarity in the x, y, and z direction. We want the model to fit in a building. We might discover that to do that, we'd have to find a liquid that has the viscosity of air and the density of mercury, and such liquids don't exist on the Earth. So at that point, a compromise might be used, or would be used. Generally, additives are added to the water to change its friction components, and we worry much more about the relative depth to friction behavior, perhaps, than the lateral behavior. Nevertheless, these physical models are still useful, even if we can't absolutely preserve dynamic similarity. So dynamic similarity by definition is achieved if geometric similarity exists, the Froude and Reynolds numbers are preserved, and the pressure coefficient is preserved. What dynamic similarity means is that the values of the pi groups in the model are equal to the values of the pi groups in the prototype. Let's consider a couple of examples, see how these ideas work out. Let's suppose we had an open channel model with geometric ratio of 5:1, and that model is operated at 6.86 cubic feet per second. So the model produces a discharge of 6.8 feet cubed per second. What's the anticipated prototype discharge in the full scale? Well, the 5:1 ratio tells us that the length scale of the model is 1 for every 5 units in the prototype. Hence, the velocity scales as the cube of those, so it's 1 in 120. The volume scales as the cube of those, so it's 1 in 125. And discharge is defined as the volume over time. So the model discharge would be volume in the model, time in the model. The prototype discharge, volume prototype, time prototype. So when we take the two flow ratios, we come up with volume ratio over volume ratio times prototype time over model time. Now, if there's been no attempt to scale time, so that we, in this example, we'll pretend that 1 minute in the model represents 1 minute in the prototype, then the only ratio remaining is the volume ratio, and we would anticipate that the prototype would have the scale ratio of 125 multiplied by the model discharge for 858 cubic feet per second. Now, that may not always be the case, and in fact we may adjust times in order to operate our model more efficiently. So let's look at another example. Let's suppose there's a 10:1 scale model constructed to study the flow patterns in the stormwater detention pond. The prototype discharge, so this is full scale, is 200 cubic feet a second, and a model that we have to work with, so our modeling laboratory, the most we can produce is 2 cubic feet per second. What's the required time ratio? So this is a different take on the similar question. The scale model is length of model over length of prototype is 1 to 10. The discharge ratio would be Q models 2, Q prototypes 200, so that's 1 in 100. And so by definition, the flow ratio is a length model over length prototype cubed, so that's 1 over 10 cubed, and the time ratio TP/Tm. And we don't know what that is yet, but we do know that we can rearrange this equation and solve for the required time ratio. So Qm over Qp times length of the prototype over length of the model cubed. Well, that's 1 for 100. 10 over 1 cubed becomes 1,000 over 100, which is 10. So what that means is that time in the model is 1/10 time of the prototype. So for every 10 real seconds in real world, our model runs for 1 second. Scaling time is often forgotten, but that's actually a very useful experimental trick. It's used by a lot of experimentalists to address this issue of how to approximate dynamic similarity. Now let's look at one more example, and the remainder then you're referred to the textbook. Let's suppose we have an 80 horsepower pump and want to supply a prototype water system. The model's built at 8-to-1 scale. A velocity of 2-to-1, a velocity ratio of 2-to-1 is anticipated. How much pump power is needed in the model? So our geometric ratio, model to prototype, is 1 to 8. Our desired velocity ratio is model to prototype is 1 to 2. That velocity ratio is length over time times length over time. So we have 1 over 8. We want to find the required time ratio, Tp over Tm, to make this product equal to a half. So we find out with the length ratio of 1/8, we need a 4-to-1 ratio to produce a velocity ratio of 2. And so that requires the time ratio, time in the model, time in the prototype, to have a 1-to-4 relationship. So what that means is every 1 second in the model represents 4 seconds at the full scale. Okay, once we have that ratio established, we can examine the force ratio. Forces in the model over the forces in the prototype is rho, velocity model, length model over time model squared. Same thing for the prototype. And if we assume that we're using the same working liquid, then from the force ratio, we have velocity ratio, length ratio, time ratio squared. We assemble all that and perform the indicated arithmetic. So that's 1 over 8 to the 4th power, 4 over 1 to the 2nd power is 16 over 84. Factor out the common terms, and we come up with a force ratio of 1 to 256. Finally, the power ratio is force per time. And again, we have the force ratio 1 over 256, the time ratio 4 to 1, the geometric ratio of 1 to 8. So we have a power ratio of 1 to 512. And what that means is that the power in the model is 1/512th the power in the prototype. Thus, the 80 horsepower prototype divided by 512 means our model only needs to generate 0.156 horsepower. So that gives us a tool to estimate the amount of power we'll need in the model. So that concludes this video. The similarity modeling is a real art, and the chapter does a nice job of explaining it, certainly better than I've done in this video. And there's a handful of experimental books on how to set up such experiments.